Okay, so today we're studying improper integrals. The definition of a definite integral, the integral from a to b of f of x dx, it requires that this interval here, a to b, be finite. You know, something like from 1 to 2, or from -4 to +5. And also, the fundamental theorem of calculus requires that f be continuous on AB. There can't be any discontinuities, no holes, no asymptotes, anything like that. Okay? So what we're going to do today is we're going to study a limit procedure for evaluating integrals that don't satisfy these two conditions. And so examples of that are like the integral from 1 to infinity of 1 over x dx, which is really interesting if you think about it, because 1 over x, that graph looks like this. And so remember, area under a curve, if you're going from 1 and going out to infinity, well, you might think that's an infinite area. In this case, it might be, but there are cases where we're going to be finding the area kind of an infinite curve, if you will, and it's going to give us a finite number. This is going to come up big time in our infinite series unit, which is next. The interval from -infinity to +infinity, definitely that's improper. The integral from 1 to 5, you might say, well, that's not improper. This is finite. But you notice right here, there's a discontinuity at 1. 1 minus 1 being 0. No zeros in the denominator. That's bad. Same deal down here. You might think, well, -2 to +2, that's fine. But -1 is inside this interval, and that creates a discontinuity. This function is undefined at -1. So to begin this, what we're going to look at is the integral from 1 to b of dx over x squared. And we're just going to rewrite this as the integral from 1 to b of x to the -2nd dx. Okay, that makes it really easy to integrate. Add 1 and divide. We're going to have -1 over x evaluated from 1 to b. And so this is -1 over b minus -1 over 1, so that's going to be +1. And that's fine. What this allows us to do is consider the integral from 1 to infinity of dx over x squared. And we're going to do this slick little trick where we're going to let this be the limit. Now, since my improperness, if you will, comes from this upper limit of integration, I'm going to use the letter b, because integrals we typically write as the integral from a to b. So the limit as b approaches infinity of the integral from 1 to b of dx over x squared. Now this we just figured out. That was right here, -1 over b plus 1. So this is the limit as b approaches infinity of -1 over b plus 1. Now here, as b approaches infinity, the denominator grows larger and larger and larger and larger. -1 divided by a larger and larger number is 0, plus 1. This limit is equal to 1. And so what you can say is that this integral, the integral from 1 to infinity of 1 over x squared dx is equal to 1. Think about that for a second. Okay? 1 over x squared looks like this. And so we are taking this area from 1 and we're going all the way out to infinity. And I'm saying that area there, and we keep on going forever and a day, is equal to 1. It's kind of cool when you think about it. All right, so definition of improper integrals with infinite limits. Oh my goodness gracious. If f is continuous on the interval a to infinity, here's what you're going to do. Okay, this is just some number here. If the infinity is the upper limit of integration, we're going to let the limit as b approaches infinity of the integral of a to b. Okay, so we're just replacing the infinity with a b. But if it's at the lower limit of integration, I just use an a. You can use any letter you want to, but you know, we're so used to writing integrals from a to b that if the infinity is in the top, I use a b. B approaches infinity. If the infinity is in the bottom, I use an a. Limit as a approaches -infinity. And then down here, if f is continuous on the interval -infinity to infinity, if you have something like this, you're going to break this up. Okay, you're going to break it up at some value for c. And you're going to go from -infinity up to that value, and then that value up to infinity. and then you're going to basically do two of these processes. So let's actually do some here. Before we move on, if the limit exists, okay, if the limit actually exists, like you get a number, like we did in the last one, if the limit exists, what we say is that this integral converges, okay? If it does not exist, like you get an infinity or a negative infinity, the limit does not exist, we're just going to write D&E shorthand, okay, then it diverges. Down here, when you do these two integrals, I should say, if one of these diverges, then the whole thing diverges. All right, let's get a better color here. Let's get some blue. All right, so we're going to evaluate the integral from 1 to infinity of dx over x. Now, obviously, infinity is the upper limit of integration, and so we're going to rewrite this as the limit. Since it's the upper limit, we'll say as b approaches infinity of the integral from 1 to b of x to the negative first dx. Well, I know what the integral of 1 over x is. It's the natural log. So this is the limit as b approaches infinity of the natural log of the absolute value of x. And this is evaluated from, I should use brackets here, from 1 to b. So this is the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. Natural log of 1, 0. And so think about, as b approaches infinity, what is the natural log doing? Natural log looks like this. And so as you approach infinity, the natural log keeps on growing. So this is equal to infinity, and therefore this integral diverges. Now this is a big thing come next unit. The integral from 1 to infinity of dx over x diverged, but the integral a couple slides back here from 1 to infinity of dx over x squared converges to 1. Okay? And so in infinite series, we're going to be talking about why that is. Okay, so the integral from 0 to infinity of e to the negative x dx. Well, upper limit of integration again, so we're going to take the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. And that is the limit as b approaches infinity. The integral of e to the negative x is negative e to the negative x, and we're evaluating from 0 to b. So this is the limit as b approaches infinity. Substituting my b, I'm going to write it as negative 1 over e to the b. Minus a negative is going to be plus. E to the 0 is 1. Now as b approaches infinity, this grows without bound. Negative 1 divided by a larger and larger and larger and larger and larger and larger number approaches 0. This is equal to 0 plus 1, which is just 1. So the integral from negative infinity to negative 1, now it's our lower limit of integration. So we're going to say this is the limit as a approaches negative infinity of the integral of from a to negative 1 of x to the negative second dx. Now before we start this, let's think about what we're doing here. We're going from negative infinity to negative 1 of 1 over x squared. We looked at that earlier. Okay, the only thing was we looked at from 1 to a positive infinity of 1 over x squared. And so that was this over here, and we said that is equal to 1. So now basically what we're doing is we're looking at this over here, and so we're pretty sure this is going to equal 1 again, because it's symmetrical. And so we're going to add 1 and divide. This is equal to the limit as a approaches negative infinity of negative 1 over x evaluated from a to negative 1. So that's the limit as a approaches negative infinity. Substitute our negative 1, you get positive 1 minus a negative plus 1 over a. And so as this grows larger and larger, as a approaches negative infinity, 1 divided by a larger and larger and larger and larger and larger and larger negative, okay, still approaches 0. This is equal to 1 plus 0. So this integral converges to 1, which is what we thought would happen. Okay, so where do you split an integral? I'm looking here, the integral from negative infinity to positive infinity. Now, I'm not too sure there's any really good values to choose from, so I'm just going to choose an easy one. I'm going to choose 0. So we're going to say that this is the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x dx. And then we're going to add to that the integral from 0 to positive infinity of e to the x over 1 plus e to the 2x dx. So now we're ready to rewrite as limits. And the other thing I'm noticing is that this is really 1 plus e to the x squared. So what I'm really thinking about here is this is going to turn out to be an arctangent. Now when I rewrite, we'll have the limit as a approaches negative infinity of the integral of from a to 0, and I'm going to go ahead, I'm going to rewrite it as 1 plus e to the x squared dx. Then we're going to add to that the limit as b approaches positive infinity of the integral from 0 to b of e to the x all over 1 plus e to the x squared dx. And as I guess, this ends up being the arctangent of e to the x. So we have the limit as a approaches negative infinity of the arctangent of e to the x. This is evaluated from a to 0. And then we add to that the limit as b approaches positive infinity. This is the arctangent of e to the x, and that's evaluated from 0 to b. So what we end up with when we do our substitution, negative infinity, this is going to be arctangent of e to the 0. Well, e to the 0 is 1, and so we have the arctangent of 1 minus the limit as a approaches negative infinity. Substitute the a, arctangent of e to the a. Starting to run out of room. Arctangent's a long word. Over here, substitute your b plus the limit as b approaches infinity of the arctangent of e to the b minus, here we go, limit b approaches infinity of arctangent of e to the 0, which is just 1. Well, here we're thinking about the angle whose tangent is 1. Okay? And for arctangent, recall that your answers are going to come from negative pi over 2 to pi over 2. So the angle whose tangent is 1 is going to be pi over 4. So the limit as a approaches negative infinity of pi over 4 is just pi over 4. right here, the limit as a approaches a negative infinity. Well, as a approaches negative infinity, okay, you're sitting there thinking, oh my goodness gracious, as a approaches negative infinity, this right here, that looks like e to the a looks like this, okay? Oh, excuse me. As a as a approaches negative infinity,